And Matt?
Okay, well, thanks for having me come in and talk with you a little bit about this. This is a topic near and dear to my heart. It's something I work on quite a bit, doing a lot of time series analysis, and you guys are learning some great new tools to be able to probe the data. I want to introduce myself briefly. I'm a geomorphologist, so that means, I'll explain what that means in a second, but I work in the Earth Lab team as a postdoctoral researcher, and in particular on the team of team erosion. And so I'm going to spend a moment here explaining to you what a geomorphologist is. And I wanted to start with the word geomorphology. It basically means somebody who studies the shape of the Earth. It's all in the root of the name. And there are basically two premises I start all my projects with. The first is that topography is a record of the types of processes that are either currently active or may no longer be active at the surface. And then even more intriguingly, the topography can record the rates of those processes that both construct and destroy landforms. So that's kind of my worldview when I come at a lot of these problems, and I'll relate that to hydrology here in a second. There's lots of tools that folks like myself use, including field observations. You might have seen, folks who do field surveys, monitoring of like stream flow, fluxes of soil, fluxes of sediment being produced, things like this. We use a lot of remote sensing. We spend a lot of time working with topography, so that means doing digital terrain analysis. Similar in spirit to some of the work you guys were doing last week, actually, only looking at the bare Earth instead. Time series analysis like I'll talk about today, and then of course numerical modeling, experimental modeling, and getting rates and dates of things using things like geochronology. There are many different kinds of geomorphologists. My primary focus is on the form and function of hill slopes and river channels, though I am similarly intrigued by coastal and wind-driven processes and glacial processes. But that's kind of my worldview on a lot of these things. And in particular today, I'm going to talk about river processes. But you might look at this landscape here. This is a photograph I took in Tibet, where we're looking down the Arun River. And so when I see a landscape like this, I ask myself, what can we actually learn about erosional processes just by looking at the morphology of this river here? And the same thing can be said, what can I learn about processes from looking at the slopes that I see, the roughness on those slopes, the maximum steepness of those slopes. You'll notice in the foreground of this image, it also shows that in some places I have soils, and other places I don't have soils. So that's a big question, because soils act as a conduit for both storing and then releasing rock that has been transformed into mobile material. And then even at shorter time scales, I'm very interested in how disturbance, like fire, for instance, can affect such longer-term processes that we might think about over the geologic record. Geomorphology is intrinsically interdisciplinary. So this is like I was taking a course many years ago, and this was my conceptual framework that I drew in that course. And of course, I put in the center of my wheel geomorphology. You can draw this many different ways. But it's my attempt at relating geomorphology to other disciplines. And in particular, topography is really interesting because it's the interface among the important spheres we like to think about: the lithosphere, the atmosphere, the hydrosphere, the biosphere. And oftentimes as geomorphologists, we're forced to think about processes that span local scales to global scales, and processes that span historic time scales all the way up to millions of years, geologic time. And so it allows us to dabble in a lot of different types of thinking in the natural sciences. Today, I'm going to particularly focus on one spoke of this wheel I drew, which is namely the interaction between climate and meteorology via hydrology, and how that interacts with the Earth's surface. And so thinking about the frequency of floods is really important for a hazard standpoint, but it's also really important to understand which events actually shape and carve the surface of the Earth. And that's why we're going to focus today mostly on extreme events, and particularly extreme rainfall events and extreme flooding events, because ultimately those are going to drive the extreme geomorphic events. And like I said, I'm going to focus a bit today on rivers because we're thinking about floods. And this sub-branch of geomorphology is called fluvial geomorphology. Many of Earth's rivers are in fact alluvial in nature. It just means they're made up of sediment. They're made up of their own deposits. This is a really dramatic example from the Mamor River in lowland Bolivia. It's a meandering channel. You can see active meanders and bars. And one of the things that a geomorphologist would see when they look at this is, wow, there's something that must be controlling the scale of these meander bends and the width of these channels. So you can think about how, again, the morphology may be encoding information about the meander wavelength, the water and sediment flux, and the floodplain width. You know, the active channel here, you may look at it and see that narrow ribbon of brown, dirty, sediment-laden water, but in fact, the active channel here is the entire width of the floodplain. But you can see those meanders are moving across quite actively. Contrastingly, we also think about other kinds of rivers that may be not made up only of their own sediment, but are also carving into bedrock. So we call these things bedrock rivers because not only do they have to transport the sediment that they're moving, but they also have to pull out and remove bedrock, which is intact rock that's sitting below that veneer of sediment. Just for scale, here's just an image of a crane, or an egret, I'm sorry. And this is the Rio Cangrejal from one of my field sites for my dissertation in Honduras. And importantly, I like this image a lot because it illustrates a number of things. One is that rivers move a lot of different sizes of sediment, which means you need different velocities and different strength of flows to actually drive the transport of, say, sand versus boulders versus actually incising into bedrock. The other thing I'd like to point out in this picture is that you can see that currently this beautiful blue river is not actually transporting very much sediment. If it were, it would be much murkier looking. It would be probably brown or gray, and that tells us that we really need to understand extreme events that are not common, to understand the long-term evolution of these systems. And so with that kind of preamble in mind, I'm gonna introduce you a little bit to my own research in thinking about how rainfall-driven floods happen, and in particular how we like to think about them for application to longer timescales. I'm going to define a few terms here. The first is a hyetograph, which you've actually already seen some of these things. This is just a plot of rainfall rate over time. It's in units of millimeters per hour. And the other is a hydrograph. It's a plot of river discharge through time. And it's in units of cubic meters per second or cubic feet per second. And you'll notice that the units are a little bit different, and that's largely because when we look at hydrograph, we're looking at how water that's accumulated over an area is fluxing through a point, versus when we measure things like rainfall, we're looking at how quickly rainfall is interfacing with the atmosphere, right? So that's why we have a length per time as compared to a volume per time. Of course, if we had that length per time times the drainage area, we get something that, and we have conservation of mass, that should turn into that volume per time. This is an important thing. So during storms, we look at hydrographs. What we're looking at is local rainfall rates. And what we really want to know is how those local rainfall rates transform into runoff, that's the hydrology of the system, in a watershed that accumulates water downstream. You can think of this in a very simplistic way. I pulled this from kind of a very well-used hydrology textbook. And it's basically the idea that we can look at any precipitation event. Here's the hyetograph on the left-hand side. Some fraction of that produces runoff, and some fraction might just infiltrate into the soil, either going to deep groundwater, maybe going to storage, maybe going to evapotranspiration. And then we have a watershed, which is actually just a transfer function that converts that storm runoff into something that we might see in a hydrograph, and that's how we get that volume per time. And so we can think about, rivers are often, at least in most places except for in the most arid deserts, have some sort of base flow, which is kind of a long delivery of water through groundwater. But when we have a big rainfall event, we get what we call the storm flow, so some additional input that we can see pretty dramatically when we look at event scale hydrographs. So that's talking about stream flow. The next thing we might want to think about is, well, what are we actually calling a flood? So I often will use these terms interchangeably. They're not really interchangeable. A flood actually has a very useful definition. We want to know when the surface that is not inundated becomes inundated, right? We don't care if a river stage moves up and down within a channel. What we do care is if I've built a building on a floodplain, or if I've got agriculture on that floodplain, when that is going to be inundated. So I pulled up a couple definitions. These are very operational definitions. So like, for instance, the FEMA definition is a general and temporary condition of partial or complete inundation of 2 or more acres of normally dry land and 2 or more properties. So this is very much wanting to know from a impact standpoint what a flood is. But we can also think of floods. This is the floodplain of the Boulder Creek. As you can see on the left-hand side is where it's coming out of the mountain front. I've got all the properties that are built properties as of a few years ago, plotted as gray polygons, and then you can see how that floodplain expands quite a bit as you get in. We have a lot of built infrastructure that's sitting on the FEMA operational floodplains. But like I said, all these are operational in the sense that we need to know how to assess hazard. We can also think of more physical thresholds, and namely the most natural one is to think about is when a river overtops its banks. And that's kind of how I like to think about it. So on average, the 1 to 2 year flood is the flood that exceeds its banks. But we can define this flood then as those flows where the stream flow exceeds the capacity of the river channel. So that's kind of a natural, because in many cases, the river is actually forming those levees that are keeping it channelized. So we can actually think about feedbacks between flooding and the morphology of the channel. To give you some dramatic imagery of this phenomenon, this is a very well-known event in 1993 along the Mississippi River. I've marked out St. Louis. You can see the sprawl. This is looking at satellite imagery from space using Earth Observatory data. And you can see the sprawl of St. Louis. The red areas are all urbanized areas. You can see the patchwork of green regular polygons that parallel the river here. Actually 3 rivers. It's where the Missouri, the Mississippi, and Illinois all conjoin. And a lot of that is agricultural land, and you can see that. But this is what happened in 1993, right? And so one of the, I think, values of being able to interpret the morphology is you can help define, even if events are rare like this 1993 event, what are the active parts of the channel. And that includes the floodplain. The floodplain is quite active. And so we're talking, 5 kilometers, 10 kilometers from the channel, you're seeing inundation during these rare events. So it's a pretty important problem to know. And this challenge scales with how big of a watershed you're looking at, what kind of climate you're in, what kind of topography you're in itself. So being able to make predictions is a really important component of doing this kind of work. You'll notice that it pinches out here. Well, the reason it pinches out around St. Louis is that we built a lot of human structures around St. Louis to protect our built infrastructure, namely levees in this case. These are not natural levees. These are human-built levees, and that's why you can see kind of the natural state of the system upstream. And then I want to make one other point. I pulled another example here. This is from the 2016 floods in Louisiana, and I've plotted up here a hyetograph on the top in orange. That is just showing the daily rainfall rates that you see, where positive is going down, so it's in millimeters per day. And then I've plotted the discharge along, I think, the Amite River that drains out into the Gulf of Mexico in blue. And you can see, for reference, I've plotted up what you're going to be doing today is calculating different event magnitudes. I just plotted up the horizontal line that represents the 3-year storm and the 3-year flood. And I like looking at time series like this in their most native form because I think it illustrates a lot of cool phenomenon and things that we need to be mindful of as we start analyzing the data more deeply. Namely, we only had, in this particular case, a 3-year rainfall event produced the 33-year flood. So it's not as simple as saying, I know what the rainfall statistics look like and I can predict what the flood statistics look like. We need other inference to make sense. And mostly we need to understand the hydrology of the system, how much water there was that saturated the soil before that rainfall event fell, how big an area was inundated with water. This particular event in 2016, yes, it was the Amite River. the 4-day rainfall totals were upwards of 450 millimeters, depending upon where you were, which led to a peak instantaneous flow, which basically is the maximum flow that was observed on the river, of 116,000 cubic feet per second, which is what the USGS reports its data in those units. Whereas the daily average flow during that event, the peak daily average flow during that event was 62,000. This is going to come up because we're going to be working with two different kinds of data. One where we're looking at events where we look at the instantaneous maxima that we see, and one where we see the daily averages. Now, they're strongly correlated with each other, but obviously if I'm measuring over 5 to 15 minutes, I'm going to get much higher rates than if I average that out over an entire day, which is going and integrating over the hydrograph. So it's good to keep that in mind as we start working with different kinds of data. The important generalizations, as I want you to remind you of as you're thinking about working with this kind of data yourself, is that intense rainfall is a necessary, but it is an insufficient condition to cause flooding. So it does cause flooding, but it's not the only thing that matters. And that's where all those other things I was talking about, things like drainage area, soil properties, seasonality, how much water was in the soil before the rainfall event happened, the size of the storm, all these things control what the runoff response is actually going to look like. So we need to be mindful of that when we start interpreting the transformed data that we're going to look at in a statistical sense. And so it actually also begs the very important question of what, if any, rainfall statistics are imprinted into the runoff statistics. And in fact, can we characterize the two together at all? So today, you're going to be working with exceedance frequency, and I'm going to explain this, I hope, hopefully relatively carefully, so that as you're going through your analysis, you can follow the logic of what we're doing. To illustrate this, I just took a stream gauge from another river. This one's in Puerto Rico, so it's in the tropics. I like using it because it illustrates why it matters over what time scale or what time interval we look at when we're analyzing data. So this is just it's just a time series from 1967 to 2006 on the Rio Espiritu, which is basically a north draining watershed in the Luquillo Mountains in Puerto Rico, which is the highest topography in Puerto Rico. It's in the northeast corner of the territory. And I'm just plotting up the data, but I'm plotting it up in 3 days, in 3 ways. The first is just as daily discharge. So in CFS, that's what you can download easily from the USGS website. The second is the red data is the monthly data. So all I've done is I've averaged by month. I've used the Julian calendar to average by month. And then the third is the annual data. So basically this is looking at what the mean annual discharge is. And they're all plotted up in CFS because they should give us the same mean because they're just different ways of binning the same data, right? So the average for every day is the same. It's just a matter of how I look at it. Just to convince you that things are very different depending upon the interval I average over, I've zoomed in here so you can see that there is a lot of variation even at the monthly and annual timescales. It's just being obscured by the fact that there's really big variation at the daily timescale. So you could apply kind of traditional statistics to this. If we looked at the annual histogram, or if we looked at just the annual frequency of different discharges, you can see the blue line is just showing what the empirical data looked like, and then I fit a normal distribution to it. So you can see it's kind of symmetric. There's a characteristic annual discharge, and that it has somewhat of a Gaussian shape to it. So let's just use a simple normal distribution to describe it. So it's not too bad at describing these observations, and I bet if we collected data for even longer, we would see that this would smooth out even more. So a lot of times you're inheriting the shortness of the record when you look at empirical data. Now, oftentimes it's convenient to, instead of plotting up the probability distribution, which is what that previous plot was, but instead plot up the cumulative probability or the complementary to the cumulative probability. So this is actually this is actual exceedance probability that we're going to be talking about later. It's also known as the complementary cumulative distribution function. The reason it's useful is because it's basically telling me for a given size event or greater, how probable is it? So you can see the max is 1, and then as you get to larger and larger events, the max, the probability goes down. And so it varies. It's a function that varies more smoothly, and so it's more useful when thinking about probabilities of some occurrence. All right, so I'm going to go through a series of these plots where I'm just showing you the same thing, only instead of using the annual data, I'm going to go to the monthly data, and then I'm going to look at the daily data. So here's the monthly data. Now note, it looks much more skewed. The mean is the same, which is unsurprising because it's the same exact data set. The standard deviation has increased, although as we get more and more skewed, the standard deviation becomes a less useful metric for us, and we'll talk a little bit more about this in a second. Monthly averages are skewed because we know that they're in every different environment. There are dry seasons, wet seasons. They have a different seasonality associated with them. So in this case, that skewness is being imposed by the fact that wet season rainfall may be just a small fraction of the year, but it's going to have very large values of discharge. So that's what we're really seeing when we see this skewness. It's a seasonal imprint on the probability distribution. Here's what it looks like in probability and the complementary cumulative probability plot. So this is the same thing as exceedance probability when we talk about it all day. Now note that when I plot it up in this way, it becomes very apparent that the tail of the distribution, so the large events, the right tail, is becoming heavier. So when people talk about heavy tail distributions, this is what they're referring to, is that more of the probability is locked up in rare large events. All right, one more example here. Here's the daily data. Now we've got really skewed data, which we could have noticed when we just looked at the raw time series, but now we've quantified it. It is reflected in a higher standard deviation, but this is clearly not a normal distribution, so standard deviation may not be the most useful metric. And now we can really see the heaviness of that tail in the complementary cumulative probability. Okay, so we start from here. We have some basic ways to view data and looking at time series that's taking it out of kind of the time domain, but instead looking at the statistical domain of what the frequency of different magnitude events are. And now I'm plotting up the same thing, only for a rainfall gauge, or a precipitation gauge, I'm sorry, and a runoff measurement based on streamflow data. So these two sites here, this is actually from Southern California in the San Gabriel Mountains. These are two exceedance probability distributions that that are taken very near each other. Now remember that precipitation is measured at a point, so its units are a little bit different typically. It's in millimeters per time. What I did to get it in the same units was I divided my discharge by drainage area, and then I get something like the same units. But notice that even when I do that, these distributions look very, very different. And that's kind of one of the fundamental questions we might ask is, well, what makes the gray curves, which are the precipitation exceedance probabilities, transform into the black dots? And the dots are the actual empirical probabilities, and the lines are just fitting a model to that, a parametric model, which we'll talk briefly about. We can also use these, now we now have a framework to compare driving variables to response variables. So in this case, the driving variable is precipitation, and the response variable is runoff. Now, this is just a moment to really emphasize this point. It's going to come throughout your exercise later this afternoon. But exceedance frequency is the probability of a given size event or greater occurring. In other words, I've been talking about it thus far as the complementary cumulative distribution function. It is not the probability of that event size occurring. That would be in the probability distribution function, right? So when someone says it's the 100-year flood, what they're saying is that this is the probability of a flood of that magnitude or greater on average occurring every 100 years. And like I just said a moment ago, that there's clearly a lot of science to do here, because you can't simply look at rainfall statistics to tell you what the runoff statistics are going to look like. And this is really just telling us that we need to understand something about hydrology. All right, so this is very redundant with what you're going to do in a little while, but the general approach of doing this kind of probability analysis is relatively straightforward. So like you guys talked about in terms of mapping out how you do any sort of code, you can think about this as a kind of a high level before we would try to implement this in practice. So all of these kinds of analysis do the same thing. They sort the data initially, and And the reason you need to sort the data is because, and sometimes it's ascending, sometimes it's descending, but the reason you need to sort the data is because the magnitudes that you're comparing are not in regular intervals. So there's some very good statistics of ranks that we can take advantage of. So once we sort it, we can rank it from 1 to n, where n is the number of observations of that data. And then we calculate this exceedance probability, and it's a pretty simple formula. It basically tells us that for the largest events, you can see the formula for yourself, but it basically tells us that for the largest event on record, it's on order the length of the record. So that n plus 1 is saying, well, if I see 100 CFS event, 100 CFS event in 100 years, well, maybe it's 1 over 101. So it's saying, well, maybe we didn't see the second largest. But people plot these things up a little bit differently, but this is the formula we're gonna use. Now, at this stage, if you have a long record, you may be happy, but you may want to actually do some things with this kind of analysis that would require you to actually come up with a model. And the reason you would do this is because, for one reason, maybe you have a short record, so you don't really care about the 20-year event. But if you only have 20 years with the data, the best you can do is say something about on order the 20-year event. The other thing you may want to do is, if you're a geologist like me, you may want to know what's the full probability distribution look like over thousands to tens of thousands of years, in which case I need some stochastic description of those events to be able to stick into my model. So this can be useful for a lot of different reasons. And then finally, we can plot all these things on in different frames. So sometimes I'll show you exceedance frequency plots, which is just probability plots. Sometimes people talk about recurrence intervals or recurrence periods. Those are simply taking 1 over the exceedance probability. So we can look at that is when we say the 1-year event, the 100-year event, the 50-year event. They're directly related to each other. It's just sometimes it's easier to think of in terms of time. And voila, you do something like this. You construct a plot. This has just got an example from precipitation, I don't even know where, on the x-axis, and exceedance probability or exceedance frequency on the y-axis. This is precipitation, so you'll notice that it doesn't go to 1, which you would expect for most exceedance probability plots. And the reason you expect this is because every event should be bigger than the smallest event on record. The reason why you don't see this on precipitation plots is because it turns out most days are dry. So there's actually a lot of probability stuck in dry days, which if I plot it up here, there should be a 0. But on log axes, you can't plot 0. So we'll just have to recognize that exists. There's a big spike in probability around 0. This is less problematic for looking at streamflow data because we usually have base flow. Okay. Quick example, because we're not going to be doing this in the activity, but I want to show you how you might fit parametric models to such data. So these are just a 4-panel map. The top left-hand corner is mean annual precipitation from 1981 to 2010, based off of this data set called PRISM. It's just the total precipitation you get in a year, total precipitation you get divided by the number of years, right? So this probably makes some intuitive sense. You know, the Gulf Coast, Pacific Northwest, those are the wettest locations in the contiguous U.S. In the next plot, I'm going to show you a couple other things. One is what you see in the top right-hand side, which is the mean storm depth. And all that is if I ignore the dry days, how big are the events that happen on average during the wet days? So I get rid of the dry days, I take my total P and I divide it by the number of wet days, and it gives me the characteristic size of rainfall events. Parallel to that, in the bottom left-hand corner, is the frequency. So this is just telling me how frequently does it rain. So I can take the top right plot and the top left and the bottom left plot to produce the top left plot, right? So I can take storm depth and storm frequency to produce mean annual precipitation. We're going to talk about this other parameter in distributions, and namely it's called the shape parameter. So it's telling us basically how heavy-tailed those exceedance probability plots look. And this bottom right-hand corner plot is showing this for analysis I did over 1,000 met stations in the contiguous U.S., some daily data. where the red colors are indicating more variable rainfall, and the blue colors are precipitation, I should say, and the blue colors are less variable. And I'll explain this more explicitly in the next figure. The thing I do want to say here is that the storm depth, the storm frequency, and the storm variability are based on point data. So I did some interpolation to try to guide your eye and then interpret these maps. But again, these kinds of measurements are typically taken at points. So we have to do something in order to figure out what's happening in between. That's why they look a little bit more splotchy than the top left-hand figure. So what I mean by fitting a parametric model is we need to have a formula that describes the relationship of our whatever thing that we're looking at. It could be X, could be precipitation, X could be discharge, X could be runoff, it could be any of these things. And it has to have some form. So in this case, I'm just saying the exceedance probability is equal to an exponential raised to the value that I care about, the variable I care about, that's also raised to a power. I'll show you in a second why this is helpful. These kinds of parametric models typically have 2 or 3 parameters that you can adjust in order to fit a distribution. One is going to be related to the mean of the distribution, and in this case, it's this x0 parameter. The other parameter is going to be related to what that tail looks like. So what's the shape of that distribution? And that's what this C value that I showed in the previous map was. So if I plot this kind of model up, where I'm just plotting my values on the x-axis, in this case I'm plotting a precipitation, so I can compare all the sites in the US. I divided my precipitation by the mean wet day precipitation so that we could kind of put them on even terms, and then just look at the shapes of the distributions. And then I've got exceedance probability on the y-axis. And you can see on this plot, I've got box and whiskers. So these box and whiskers are simply empirical assessments of how these distributions look. So 50% of data falls in between the green bar, right? The little numbers at the end are telling me if there's outliers on either sides of the whiskers. And one of the things you should notice is in the case of this particular parametric model, it looks just like a simple exponential model if this value of C goes to 1. And so this is a useful space for us to look at it because we see that, well, daily rainfall typically is heavier tailed, where these values of C go down, than the exponential distribution. So there's a higher probability of big events than you might get if you just predicted from an exponential model. And it looks like there's some sort of median or mean value that describes a lot of the data. So somewhere between C is equal to 2/3 and maybe C is equal to 5/6 is where you get that most common value. And these models matter a lot because if you're going to extrapolate beyond the historic record, then you need which model you choose has a big implication on whether you call the 100-year event 100 CFS, 1,000 CFS, or 10,000 CFS. In this case, I'm showing you just 2 different models. You don't need to know the details. These 2 different models, the blue model is a commonly used rainfall model. It's called the gamma distribution. The red model is the stretched exponential distribution I'm showing you here and the above. And then I'm showing the cloud of data that we observe from those 1,000 stations in the contiguous US. And what I've plotted here is they make predictions on the relationship between one percentile to another. So in this case, I'm plotting up the 95th percentile on the x-axis and the 99.5 percentile on the y-axis. So rarer events on the y-axis. You can see the frequency of rare events goes up as I start spinning off from the gamma distribution. Okay, let me just check my time here for a second. Okay, good. So how can we use these kinds of tools in application to, say, the Colorado Front Range, which is what you guys are going to be looking at in just a few minutes. So that's what I'm going to show you here. This is actually primarily the work that I'm doing now here at Earth Lab, is to look at how we can look at rainfall and runoff statistics to say something intelligent about the long-term evolution of the Colorado Front Range. To orient you here a little bit, hopefully you guys have all enjoyed the Front Range and gotten to get acquainted with the diverse kind of topography along the Front Range. But there's kind of 3 domains you really need to think about. One is the glaciated high peaks. So when you go up to Rocky Mountain National Park, those are landscapes that largely have inherited the legacy of the last glacial maximum. So if we're trying to predict how rivers erode, they've kind of been erased of any record. But below those high glaciated peaks, there's actually this really interesting high elevation, low relief surface. So low relief is just how rugged the landscape is. That we think is a relic from a time past, and more recently, rivers have started to incise into the Colorado Front Range, and these low relief surfaces have been left behind. Eventually, they'll be eaten up as the rivers adjust to the new uplift rates or climate conditions. And then, of course, we're out here right on that transition from the high plains into the Rocky Mountains. This is a really hot topic. There's two components of this problem that are really hot in the geomorphic community. One is thinking about how topography feeds back into the role of the amount of precipitation and the phase of precipitation. So thinking about snow versus rain precipitation. So I just threw a couple papers that are kind of been a big impetus for kind of doing this work. And the other thing that's been really kind of revealing is we've started to learn that if we can have simple models of river incision that just start incorporating some of these stochastic elements, so these random elements, and they can make much better predictions over the long-term evolution of river channels. So that's kind of the two big things that have motivated my own research here along the Colorado Front Range. I want to quickly orient you to the hydroclimate of the Front Range. So this is just a time series again. We're looking at discharge on the y-axis and going from 2010 to 2015. Hopefully you can see a few things that look regular and a few things that look odd. The first is you see seasonal snowmelt, right? So that's what these pulses are going on, right? Every year we get a snowmelt signature. Some years we have low snowmelt, and sometimes we'll get rain on snow events. So a lot of these spikes that are sitting on top of that seasonal signature are actually rain on snow events or extreme melt events in some cases. But sometimes we get really big events that are well beyond the snowmelt season. So you can see that in 2013, we actually had a really low snowmelt signal. And the timing of that event actually occurred well on the tail of it. So there was very little contribution of snowmelt to that event. It was all about the rain in that particular case. And so when we think about interpreting our statistics, this is kind of the worldview we need to start thinking about, is what processes are driving those really big and rare events. Is it snowmelt events? Was this an anomaly? Did 2013 represent the long-term behavior of this kind of system or not? To look at it another way, this is just a map of that 2013 rainfall event. It's the radar precipitation is kind of overlaid on a hillshade, so you kind of get a sense of the topography, and I've marked a few places where their cities are. And then I've highlighted a contour which happens to be the 2,300 meter contour. So about where you get up onto that low relief surface. So you can see where that rainfall event really focused. It was basically right along the transition from the high plains near Boulder, but then there's another pocket that was centered kind of near that 2,300 meter transition just to the northwest of Boulder. And to give you some sense, this is a 7-day rainfall, I should say, of how significant this event was. I've just plotted up what's called a swath profile. So I'm plotting up precipitation on the y-axis and then distance from west to east on the x-axis, and where that box is on the map. And you can see, unsurprisingly, median of precipitation peaks near the divide. That's where we get most of our snow. It's upwards of about 1 meter per year up there, and then by the time we get to the plains, we're dropping below 400 millimeters per year. But that single rainfall event, the 7-day totals that I got from the National Weather Service, basically accounted for 75% of the annual budget for that position along the rainfront. So it was a very important event that was much larger than what we would typically expect. Another way to look at that, and this is another way to look at exceedance probability that the National Weather Service spits out. They have their own estimates of exceedance probabilities, is they plot up these contours of annual exceedance probability. So in fact, that's what you're looking at on this plot from the National Weather Service. They pick interval averaging timescale, so just like I was talking about the daily event that's shown as 24-hour event here. And then they've plotted up just the precipitation magnitudes in inches on the y-axis. And they show these contours for what the 10-year event, 50-year event, 100-year event, 200-year event, 500-year event, 1,000-year event are estimated to be. And then it shows what the properties and characteristics of that 2013 event were. And so what you can see is that at 12 hours or 24 hours, it was a rare and pretty significant event. But what made it truly rare was when you looked over a longer time averaging interval. So this was a really long duration and large spatial scale event, which is what really made this the 1,000-year storm. Importantly, for thinking about both the geology and the hazard, is these landslides removed hundreds to thousands of years of hill slope weathering products. So that was a really big deal. I mean, it triggered a lot of landslides right along the Front Range. It also produced massive flooding. And so that's the data set you're going to be looking at. So these are just some images from the local newspapers along with St. Vrain. And the most significant rivers were generated along the steep mountain front. All right, I'm just going to skip here. This is just more details about this particular event. And I just want to show you the a different kind of event, but that may be just as significant. So in any case, this 2013 event was not a 1,000-year flood. It was more like a 200 or 100-year flood. But that's not to say it wasn't a 1,000-year event, because what you care about dictates how you might describe it. So, and in particular, the processes you're interested in. So this may have not been the 1,000-year flooding event, but it may have been the 1,000-year landsliding event, right? So it's important to be clear when we start putting probabilities on things, what process are we actually trying to explain? Because it's not straightforward that the 1,000-year storm is going to produce a 1,000-year flood. Now, I just want to show you one other event because we're super lucky to catch it here. Some of my collaborators in Earth Lab, we're fortunate at University of Colorado that we are part of the Critical Zone Observatory Network. We happen to have a small catchment gauged along Boulder Creek that was heavily instrumented. So it's got rain gauges, it's got a little flume so we can measure discharge in this really small side tributary of Boulder Creek. And when I first got here, this event happened in 2016 where it had much higher rainfall rates but had a much smaller spatial footprint and had much shorter duration. It was associated with this intense convective activity that just happened to occur over our CZO monitoring site. And the only point I'll make is that if you look at the spacing of places where we have sub-daily rainfall estimates, that's where all the points on my map are, it's about the scale of the size of the footprint of the storm. So we were just barely able to capture the peak here. So these kinds of events are probably pretty underestimated in a lot of our analyses because we don't have the spatial density to be able to resolve them. Importantly, it triggered a lot of interesting geomorphology. So typically you don't get this kind of erosion, which is in this kind of landscape, namely overland flow that then erodes the hillsides via these small rills. You see rills all the time when you go to a construction site after a big rainfall event. Those are impermeable surfaces or relatively impermeable surfaces that start getting little channels that form in them. Well, this small convective event actually produced a lot of rills in this small catchment that removed hundreds to thousands of years of weathering products, just like that 2013 event. Now, it only happened over a small area, but that process was able to remove hundreds to thousands of years of soil. And this is just a map showing where those rills occurred. All right, and this is the last slide I really want to show you, which is simply that we spend time thinking about what different kinds of exceedance probabilities are, whether it be for floods or rainfall, but it really does matter over what timescales we care about. So this is those same two events I just talked about descriptively. The red data is showing the 2-minute rainfall throughout that 2016 event at the Patasso site, and the blue data is showing the 2-minute rainfall for the 2013 event. And then I've also got the 15-minute rates, which are just smoothed over those spikes in the solid lines. And so hopefully you can see here that, the peak intensities during that one event were at least a factor of 2 larger, but it didn't last very long. It only lasted for an hour. So what matters to you when you do these kinds of analyses is actually really reflective of what process response, like landslides, rilling, flooding, that are going on in your landscape. And so we can use these kinds of analyses, these more sophisticated time series analyses, to suss out intensity, duration, scale relationships, and also to figure out if there are erosion and runoff thresholds that are very important to the evolution of our landscapes and to the evolution of hazards. It's hard to do this kind of work because by definition, rare events do not occur very often. And more importantly, even if we could predict rare rainfall events, it's not as simple as them directly translating into rare flooding events or rare landsliding events or whatever we're interested in. And so it is actually a really big challenge because we don't have a lot of data with which to really validate our models. So usually we're forced to come up with some sort of stochastic description of these kinds of relationships. And that's in fact what you guys are going to be doing. You guys are going to be doing in the context of looking at floodage frequencies along Boulder Creek, which I think is very germane to these examples I've shown today. So I'll just leave it there. Thanks.